HGeom0802. Title of today's lesson is Similar Polygons. So we need to think about when are polygons similar? And notice we're straying from the path of congruent polygons, which is what we spent most of the first trimester studying. All right, same shape is idea number one, and different sizes. Now the shape refers to the angles and the sizes refer to the sides. Now when we think about these sides need to have a ratio between them. And that ratio between them has to be, important word, constant. If we call that ratio, say, x over y, some random ratio, it doesn't matter whether this is going to come up later on, it's actually a theorem, this section. Whether we're dealing with a side or a perimeter, the ratio will be the same, x is to y. But the area, and this is coming up in a future section, will be x squared to y squared. Yeah? All right. It's like look at two triangles here that have that are similar, declared similar, and we can see that the angles are all the same. Then we need to think about, like, is this similarity going this direction or is the similarity going this direction? Because our ratio could be expressed two different ways. It could be expressed as x over y or y over x. Let me take a drink here. Ooh, okay. All right, so if it's x over y, that would mean that we're going to something smaller, okay, and that would then be written as 12 sevenths, if we're comparing x to y. And that would be going then in this direction. Okay, if you're going as y over x, that would be 7/12. Whoops. Sorry about that, 12 sevenths. If we're going from y is to x, if that's the ratio, then notice the y is smaller than the x, therefore we have 7/12. So keep in mind there's two different ways to interpret that. If there's no indication in the problem, you can assume it's going left to right. So this would be the default direction. All right. Dilation is the process of making something larger. So that would be, in the previous problem, going from right to left. Your pupil dilates. And one way we know that by looking at just the ratio is that 12 sevenths is bigger than 1. And we know that 1 is a representation of 100%. Had the dilation, or had the ratio been 12/12, that would have been exactly 1, and that would mean then that the sides don't change, right? All right, going the other way, we call that a reduction, and that would be making something smaller. I've done a different example here. Capital R and a small r in two different font sizes. Measuring the heights of them, it's 16/24. Notice how that ratio is less than 1. In other words, the numerator is smaller than the denominator. Just make sure that you reduce your ratios, 2/3. And notice how 2/3 is less than 1. All right. So, proving shapes are similar. There's two parts to this. Sides, again, have to be, as we said previously, proportional. And the angles are congruent. All right. Our first example. Notice they give us a statement. A, B, C, similar to. Again, note the symbol for similarity is similar to triangle DEF. Now I've highlighted the 6 and the 12. because I can see in the not in the diagram, but in the statement, A and C correspond to D and F. And so that's how I know the 6 and the 12 are corresponding pieces. Now certainly the diagram shows us that as well, but make sure that you always go off of the statement. So we can set up the ratios to prove that these two are similar. 4 is to 8, as 6 is to 12, as 5 is to 10. And notice all those ratios stay constant. They're all 1/2. Okay? We could have flipped these ratios around too. When I'm proving that the sides are proportional, it doesn't really matter how you start off, whether you go with 8/4 or 4/8. Okay? Triangle MCN is the dilation of triangle MED. Notice triangle MED here in this case is larger. Sorry, MED is the smaller one, MCN is the larger one. And the ratio is 2 to 1. And they said find the lengths of the sides of MCN. Well, it isn't too difficult to find side MN, that's 6, and side CM, that's 8. We then can use Pythagoras to help us find CN, in which case we get x squared is 100, so x is 10, not -10, correct? Keep in mind we could have also used what's known as a triple. That is, if you know two sides and they both happen to be legs, and they're 3 and 4, then we know that the third side has to be, the hypotenuse has to be 5. And if I multiply those all by 2, we have a related, what we call a triple, 6, 8, 10. All right. Again, if we're given a quadrilateral is, let me erase some of these things here, apologies. Similar to another quadrilateral, and it says find the sides. I'm going to label the sides X, Y, and W. First of all, know that which sides you begin with. So for example, if I'm trying to find X, I want to come over to the corresponding piece and find the corresponding piece. How do I know 4 and X are corresponding? Because if we look at BC here and FG there, they're in the same positions. You can start with either 6 is to 9 or 9 is to 6. Doesn't matter. I'm gonna choose 9 is to 6. I reduce that to 3/2. And so we say 3 is to 2 as X is to 4. And solving that problem, most of us don't need to work too hard to figure that one out. X is 6. All right. And likewise, then going for Y, for example. Again, starting with the ratio 3/2. That's our constant ratio between the sides. And then setting that up equal to Y/3. Notice the Y is on top because that's the larger piece. The 3, the corresponding part, DC, yes, is the smaller piece. Solving that, we get 9/2. I'm not going to find Z, W, it's the same process. All right, little star around this theorem. An important concept, especially as we build to the future, that these perimeters between similar figures are also proportional. Meaning, if you know the ratio between the sides, you know the ratio between the perimeters. And an example of that is this last problem. If we could find the perimeter of the larger quadrilateral without figuring out W. And that's because if we add up the sides here, we get a perimeter of 20. And so I come over here and I say, well, the perimeter of that one has to be in the same ratio of 2 to 3. So multiply that by 10. The perimeter of this one has to be 30. Yeah? All right. Turn off that news there. Sorry about that. Here now we've got angles given to us in these triangles. Remember, the angles have to be congruent, not proportional. So we find measure of angle K. Again, we go to the diagram when we say, okay, or not the diagram, but the statement. K and M are the same. So notice here I have K and M the same. And we know that if we look at M, M says it's x plus 5. And K, we don't know. We do know that the angles of a triangle add up to 180. And if I subtract 90, and if I subtract 40, I think I get 50. So if I set x plus 5 is equal to 50, I think we can figure out x is 45. Likewise, for y, angle O, we can see is appears to be the right, no, it is the right angle because H and O are the corresponding pieces in our statement up there. So angle O must be 90, and that's 1/2 y. And so solving this, we get y to be 180. All right. Our final problem. Given triangle BAT and triangle DOT are similar, and they're put back to back, then they're asking you to find the value of x, which is AO. Yeah, that's that little piece up there. So again, finding corresponding sides. Hopefully you can see that one triangle has a height of 15, that's the smaller one, and has a base of 9. The other triangle, we don't know how high it is. I'm going to call it 15 plus x though. And then the base is 12. You could solve that proportion there, multiply your extremes and means. But before you do that, if you happen to notice, the 15 and the 9 both reduce, yes, to 5/3. Now, if I do the extremes and means, the numbers are smaller, my chances of making mistakes are less. And we get 45 plus 3x is equal to 60. So 3x is 15, so x is 5. Bingo, we found the answer. All right? Well, good.